Hello, my name is Pol del Aguila Pla, and I'm a research staff scientist at the CABN Center for Biomedical Imaging in Switzerland, and a postdoctoral researcher at the EPFL's Biomedical Imaging. And I'm here today to present to you the work we published in IEEE Signal Processing Letters, entitled Convex Quantization Preserves Log-Concavity. So the title sounds a little bit mysterious, but if you follow here, you'll see that what we're really trying to solve is a very common problem in signal processing, which is that the reality of our signals is that we have quantized signals, such as these examples here. So for this one is, for example, from biomedical imaging, where in PET scanners, you have sine-grain domain measurements, but they're quantized according to the geometry of the PET scanner. Or in high energy physics, you have like energy detections that are discretized according to honeycomb electrode detectors, or maybe more traditionally in signal processing, you simply have independent analog to digital converters in each dimension, and therefore your quantization of the multidimensional space looks like these three-dimensional boxes. But while we have this type of data, we almost always ignore it, and we have our models are continuous. So here is the expression for a generic model driven by some kind of noise, which we call W. And what we typically want to estimate from those linear models are this location parameter X, which we may be observing through a rectangular matrix S. And then the scale parameter, this psi also, which we restrict here to be a positive definite matrix as customary in statistics. And why is that a problem? Why is it a problem to use continuous models when we're actually trying to extract information from quantized data? So as we can see in this plot here, we do this exactly for a Gaussian. So we use the continuous model of a random normal multivariate normal distribution, but we use it on continuous data and on quantized data. And you see that the mean square error gets substantially worse, especially when we're trying to estimate the covariance matrix. So in this case, the scale parameter, as the discretization gets harder, gets coarser and coarser. So for example, when the discretization grid equals the size of the largest eigenvalue of the sigma matrix we're trying to estimate, we see that we're losing 6 dBs with respect to the case where we actually have continuous multivariate normal data. So then we look at the central question within this framework, which is basically trying to answer why wouldn't or can you use a quantized model instead for the estimation so that you don't get exposed to these effects. Because intuitively, when you first encounter this problem, you may try to write the likelihood of the real quantized data, and you may think that that likelihood maybe won't have good properties. So basically, our paper is about showing that the resulting likelihood is actually log concave. So that means that it's amenable to many of the techniques that we traditionally use on continuous models. They can be directly applied on the quantized likelihood, which will be slightly more cumbersome to write, and therefore some of the expressions may be more cumbersome, but it still has good properties in terms of that it is log concave with respect to the location and the scale parameter under a very wide range of conditions, which basically the most important requirement is that the quantizer that one uses for the data has to be complex. So if you want to know more about this, you want to know a bit how to visualize these things, our particular results, or exactly what is the math behind our results, I encourage you to come to our poster in Greece, and I'm hoping to see you there. Bye-bye.